Bismillahirrahmanirrahim. Assalamu alaikum viewers, and in this video we are going to understand the geometrical interpretation of our single variable function, because you know that in your pure maths, in your A-level syllabus, you are simply studying the basic of your integration, which is of course single variable or single integration involving a function which is of one variable, okay, or a one variable integrand. So you see, if you do not understand the geometrical interpretation of your integration, you won't be able to understand its application, right? So if you don't understand the application, then no matter you are gaining mastery in all the methods of a single variable integration, it's not going to help you out in your advanced level, okay? You won't be able to understand the advanced double or triple integration out there. So if you if you just adopt high advanced calculus in your higher standards. So you see here we are going to understand the geometrical significance of single variable integration, and that's the major objective of this video. And then of course we are going to pick a few examples related to the application of your integration. So you see, in the beginning I must tell you that the application or the benefit of your single variable integration is to find out area under the curve. Area under the curve, okay? So how you're able to find it out, okay, and how this formula is helping us out in calculating the area under the curve. You should know the background, right? So for that purpose, I'm going to draw here a nice first quadrant of my two-dimensional plane, and like that. And I just pick up a general function, any function. It could be a polynomial, it could be logarithmic, exponential, trigonometric. You just pick up any function you want, okay, and you just plot it and you get a graph of that function, okay. So I just represent here a general function, and I say that when I plot its graph, it is giving me a curve something like this. It's just for instance, okay. That's how it is. And something like this, okay. Now I just say that on this curve I just pick up 2 points which are far distant apart from each other, and you can easily observe that they're quite visible and quite far away from each other, okay, right now. So you see, now I'm going to assign the coordinates, and I just assume that let the coordinates of my P are it could be x1, y1, right? And the coordinates of my Q are said to be what? I think instead of taking these variables, I just say that the coordinates of my P are A and B, and the coordinates of my Q are CD. Okay, so now I'm going to follow projection from point P and point Q on my x-axis, and that's how it looks like. Okay. Like that. Okay, now what I want here is to find out the area bounded by this arc PQ. Okay, the portion of the curve or the segment of the curve is called the arc, you know. So I need to find out the region, the area of a certain region which is bounded by this arc PQ. I can call it like that. And this line which is x equals to A, the line x equals to C, which is this, and the segment on my x-axis which is starting from this point A and ending at point C. So actually I need to find out area of this region, alright, or a template is called area under the curve. So how you're going to find that out? So for that purpose, what I do, I just prefer to draw couple of rectangles here of equal widths. Okay, so it looks something like this here, something like this. Okay, so I just say that here I'm having these rectangles look too beautiful, I must say, but instead of you see these rectangles are also exceeding from this particular arc PQ, right? A portion of these rectangles are going outside. So if I just try to find out all the areas of all these rectangles and I just try to sum them up, then the summation is going to include these unwanted areas as well. So it is going to bring kind of error in my calculation, right? So I need to minimize, I need to finish that error. So for that purpose, what I do before making that approach, I just make one thing clear further ahead, that how you sum up the area of all these rectangles. You see, I know that all these rectangles are having same width. Okay, so I just say that, for example, if this is my x1, this is my x2, this is my x3, this is my x4, and here I'm having my c. So it looks something like this. So you see the distance that I so obtained, which is this one, which is called the width of my rectangle. How it is obtained? It is actually obtained by subtracting the length x1. Length x1 is actually this, right? From starting from this point and ending at this point, right? And I am subtracting my length a1, my length a, which is starting from the origin and ending over here. So I subtract this length from my x1 length. So what I'm getting now? I'm getting this much length left, which is the width of the rectangle, am I right? So I represent the difference of two lengths as my del x, and del x is actually representing the width of my rectangle. Alright, I know that the area of the rectangle is length into breadth. Breadth has been specified, it is del x, and it is constant throughout all the rectangles. That's okay, but rectangle to rectangle, my height is varying, right? Every rectangle is having different height because the curve is quite curvy, you see. So it's like that. So you see, if I talk about my first rectangle, the first rectangle is having x coordinate over here. Okay, this is the second x coordinate. So I just try to find out its corresponding y coordinate here. It is mapping somewhere here. I call it y1. Alright, so this y1 is actually your f of x1, and f of x1 is actually representing the height of this first rectangle, right? So area of the first rectangle a1 is actually equals to my length of the rectangle into width of that rectangle. Similarly, talk about the area of the second rectangle. This is the breadth of the second rectangle, and as far as the length is concerned, you just pick up this point, find out its corresponding y coordinates mapping somewhere here perhaps. So it is y2, and y2 is your f of x2, and f of x2 is representing length of your second rectangle. So this is going to be the area of the second rectangle, length into breadth, something like that. So in the same way, you keep on finding out areas of all the rectangles which are present inside this region. Okay, so that's how it goes on, and then you sum up all these rectangles. You are then going to find out the area under the curve. Alright, like that, a1 plus a2 and so on. What's going on? Now you see, if the width of the rectangle is broader, then there's a clear chance that these rectangles are going to exceed, or they will go beyond the curve, right? So it is going to bring error, as I told you already in the beginning. Okay, that's how it is going beyond the curve, and these portions are also going to be add up in these areas, and that's why I'm not going to get the exact area under the curve. So I need to minimize this error. For that purpose, what I do, I am going to shrink the width of my rectangles. So of course this thing is going to increase the number of rectangles within the region, right? So if I decrease my del x so small that I must say that del x is extremely small, that it is tending towards 0. Make sure I just use here tending term. It means that del x is not equal to 0, it is getting closer and closer to 0. Okay, so del x would be 0.0000 up to million zeros and then 1. Okay, so it's extremely small, that's what I mean. So if I just shrink my width, then this is going to minimize the error. So how it looks like, it looks something like this. Well, that's how it looks like. Okay, I increased the number of rectangles, so I just say that let n be the number of rectangles. I'm increasing them so much that they are tending towards infinity. So it means that this thing is possible only if my breadth of the rectangle is extremely small, right, tending towards 0. That's the relationship. So in this way you can see that a very small or negligible portion of the rectangles are exceeding the curve. So if you keep on increasing the number of rectangles, the width will keep on decreasing. So in this way the error will get completely diminished. Alright, so I hope it's clear. So that's the process that we are just going to that's the concept that we are going to use here in order to understand the formula of the integration. So you see what exactly we are doing here in case of representing our area. As I'm having infinite number of rectangles, so infinite areas I'm having, right? So this is exactly what is happening. I'm going to write hardly 2 or 3 areas, something like that, and then I just continue it. That's how I represent. So you see, I'm having I just take out my common width, which is of course it is constant throughout, so I just take it out common outside. Inside the bracket, what is left are infinite number of my lengths of infinite rectangles. So I'm going to take out the summation of all these lengths. Alright, that's what I'm going to do. So you see, as I'm having infinite number of lengths, so instead of writing like that, I prefer to write it in terms of my Greek summation. Okay, so n is going from 1 to infinity, and n is representing number of rectangles. So n is moving from 1 to infinity. F of x and n is written here in the subscript. That means that this thing is actually representing this full thing. Okay, so that's what exactly it is interpreting. So this is equal into del x. That's it. So this definition is actually representing this situation. All right. Now what I do, I'm saying that if n is infinite in number, it means the width is also going to be extremely small. So I'm going to apply here a limit. The limit is actually going to explain us that breadth is not actually 0, it is tending towards 0. So I'm going to explain this thing, or I'm going to emphasize this thing by placing the limit. So I just place a limit here, and the rest of the thing I just copy as it is. Alright, like that. So once when I apply the limit, now there is no need to write this Greek summation summation letter, that what we call sigma. There is no need to write it any further. We are going to replace this limit and the sigma thing by elongated s. Okay, you know that integration is actually representing what? It is actually taken in the sense of summation, in a literal sense, right? So from the summation s, what I do, I just pick up that s and I stretch it a little. I stretch it a little in such a way that it turns into a form of a hook. Okay, so this summation s, or an elongated S is representing integration sign, okay? And I just represent my f of x n simply by f of x, and this del x, or difference in the breadth of the rectangle, by applying the limit is going to be transformed into differential. Okay, so we just represent this del x after attaching the limit with it. It is going to be represented by dx. Okay, so this is the differential thing. But that's how the formula has been derived, and this formula is going to help you to find out area under the curve bounded by interval on the x-axis from A to C. Okay, I have just restricted the bottom of this portion of this plane by AC line segment on the x-axis. So you see A and C are representing upper and lower limit of this integral. Okay, because if I don't assign here my x-axis limit, then of course this curve is going to be extend far beyond here and there, and I'm going to have an infinite area. Okay, so I need to find out a specific area bounded by this interval on the x-axis, right? So this is actually the upper and lower bound of the integral, and I just write it like that. Okay, so I hope till here the concept is clear at how you find out area under the curve with the help of your integration. Now in the next step, as you might have studied in your books, you might have seen this formula that the definite integral is actually that integral in which the limits are well defined, and definite integral is actually find out with the help of this formula, f of c minus f of b. And normally people use b over here instead of c, so it is f of b minus f of a, just like that. So how this formula has been derived, you should understand that first, and after that we just move to the respective examples then. So you see how this formula has been derived, that's a concept to be understood first. So for that purpose I'm going to draw another nice graph that is going to help us out. So let's have a look. Now you see here I just maintain a part of the curve, and I have just developed the projection from the point P and Q just like I did before. Now what I do here, I just say that let there is another point over here between my P and Q somewhere. I just call it, for example, there is another point over here, I call it R. Okay, so these are the coordinates of my P and Q. The x coordinate of my P and Q are A and C, as I told before. So now what is the and I must move my R a little over here, so it's much better for me to sketch the image at the second stage. So I just say let R is over here a little, okay, like that. And I'm going to follow a projection from R on my x-axis as well, something like that. Okay, and I just say that let the x coordinate of my R is x, nothing else. Okay, now you see I know that the y coordinate of my P is somewhere here, which is B. Okay, and the y coordinate of my R means once when my P is approaching towards R, or maybe you just say that there is a certain point R on the curve and its y coordinate is y, and the y coordinate of my Q is D. Well, that's quite well defined. Okay, so what exactly we are doing, I am now going to understand here the area concept, right? So if I say that if this is a certain rectangle, for instance, okay, and it is having a certain breadth, certain length, and is giving me a certain area, of course. Okay, now if I say that if breadth is increased up to little over here at the distance at the concept of my del x, means if I increase a small del x length here, then of course there will be a small change in my del y, in my y coordinate as well. It is also going to increase a little over here. So this thing is going to bring overall impact in the area of this new rectangle represented by the dotted line. Okay, this is my del y. So you see, this is going to be a new length, this is going to be the new breadth, and this overall rectangle is going to give me a new area, which is a plus del a. Are you getting it? So if the breadth has been increased a little by means of my del x, so the length is also going to be increased, of course, in terms of my del y because of its connection with the curve. This is going to bring a slight change in the del a as well. So if del x is extremely small, then this is going to bring very small change in del y as well. And as both these changes are extremely small, so area is also going to be changed to a very small extent. Okay, something like that. So now what I do here, I just say that let there is a certain rectangle over here I just developed by joining this point P over here on this axis, and I call this point as my T, for example. And then I am going to join my R, or I'm going to develop my I'm going to draw a line from my R, and I will stop right above my P. Okay, and I just join this line, something like that. So you see now, and I call this point as my S, this point as my S. So now you see, if you talk about this small rectangle over here, it is having, just assume that it is having a certain area A1. Alright, I just move here. Okay, and this area A1 is actually the product of this length, this breadth, which is my del x from here to here. This is my del x, and the breadth and the length, the length is from here to here, which is actually equals to b, right? So this a1 is equals to length into breadth. I hope it's clear. Now what I do, I'm going to pick up here. Instead of picking up, I just remove this line now. Okay, and I just talk about area bounded by the curve PR. So this one. So this area is actually equals to what? It is actually equals to my same breadth multiply by this much length, because you see that the bigger line of this region is actually having the length equals to y, right? So my A2, I just call this area as my A2, and it is equals to y multiplied by del x. Now the question comes in mind that while between b and y there is a difference, and we call that difference as our del y, right? So in other words, you can also say that y is equals to b plus del y. So I can replace my y by b plus del y multiplied by del x. This is my A2. I hope it's clear till here. Now what we do, we are just going to focus on this big rectangle. So this big rectangle is now having same width, of course, that is del x, and its length is equals to same thing. Its length is also b plus del y, of course. So we just say that A3 is equals to b plus del y, that is the length of this big rectangle, okay, and times del x. That's it. Okay, I just messed up a little. My a1 and a3 are perfectly fine, but as far as my a2 is concerned, it is bounded by the curve PR, so I cannot use here rectangle formula, of course. So I just assume that let the area bounded by this curve PR and these two lines, x equals to a and x equals to simply x, you see. So I just represent it by my a2, or I can represent it by my del a. Okay, so here I cannot use here, of course, my rectangle formula. I just call that let a2 is my del a. Okay, so this area is actually my del a. Alright, so now you can see that a1 is less than my del a, which is a2, and is less than my a3. That's the figure is telling us. So now we are going to rewrite this inequality in terms of their length into breadth formula and so forth. So it is going to look something like this. Now, as I told you in the beginning, that once there is a small change in x, then there will be small change in y. So if I apply the limit that if del is approaching to 0, then del x is approaching to 0, then del y is also approaching to 0. Okay, it's something like this. Now, before applying the limit, because if you directly apply the limit at this stage, then of course this the upper bound and the lower bound of the inequality is going to be 0, so we don't want that. So what we do, first of all, we are going to divide the entire inequality by our del x. So it is going to be equals to something like this. So it will be del a upon del x, and this will be b plus del y. Alright, and then we can simply write the corresponding variable limit over here. And here in the lower bound, we are simply having constant value b. So even when we apply the limit, there is going to be no impact in the lower bound, because over here we are simply having b here. So once when we apply the limit, we are having a concept that it will remain as it is. As far as this is concerned, once when we apply the limit y tending to 0, this del y will get vanished and simply b is left. And once when you just apply the limit on this ratio of the differential, then it will turn into a derivative representator that you call del operator, and it is equals to del x, del a upon dA upon dx. So now, according to your sandwich theorem, it says that if your upper bound and the lower bound are same, then this thing reveals that the corresponding parameter is equal to that value. Alright, that's it. Now, as I told you in the beginning, that b was actually equal to b was actually representing the y coordinate of my point P. So b is actually y coordinate. So if I further generalize this definition, I come to know that dA upon dx is equals to y. I hope it's clear till this point. So you see, the rate of change of area of the certain region is actually helping us out in calculating the length of the boundary so covered. How? You see, if this is a curve, okay, and this is a point P and this is point Q, alright, so once if your P and Q is having a certain certain breadth, that's what you call del x. So if there is a small change in del x, then there is going to be a small change in our entire area. So we come to know that this point Q has covered over here. So overall, we just determine or we just come to know that how much area has been covered or how much length of the curve has been covered once we observe the change in the area. Okay, the change in the area helps us in finding out the area covered by this curve, or finding out the length of the boundary covered by this curve. Okay, okay, now what we do, we just say that we know that y is actually equals to our f of x. Alright, fine. So if I take integral on both sides of this equation number 1, like that. Okay, so and I know that my f of y is equals to f of x, so it can be written like that. And as different derivative is the inverse of our integration, so once both these functions are combined, they are going to cancel out each other's effect, and what is left is the parameter. So here simply a parameter or area is left. So now once when we apply the integration, you are going to have another function over here plus some constant. Okay, so because presently here we haven't applied the integral limits right now. Now I just say that I'm having a situation, and according to that situation I'm having a certain curve, and that curve is intersecting my x-axis at point A, and at point B it is somewhere above or below, maybe. Okay, like that. So whenever x is over here, if x value is if the value of x is over here on the x-axis in such a way that the curve is intersecting that value, so it means the area at that point is 0. Okay, so at area at x equals to a point is 0, right? So if at x equals to a, your area is 0, right? So it means if I pick up my equation, this one, my area is 0, so f of a plus c, so c constant is equals to minus f of a. And then I say that what is going to be my area at point B? So I just say that at point B it is going to be f of b plus c, so it is going to be f of b minus f of c, because c is equals to minus f of a. So like that. So this is the formula of your definite integral according to your first calculus, first fundamental theorem of calculus. So area, which is so calculated by means of this integral, is equals to your f of b minus f of a. I hope it's clear. So we are now going to use this formula in order to find out area under the curve, and we pick up 2 examples here now. So here you go, this is the very first example here. We need to find out the area bounded by this function and the lines x equals to minus 1 and x equals to 2, and the x-axis, of course. So you see we are going to use the above formula that we have just discussed. So I just say that area under this curve is going to be calculated by the help of this definite integral. Okay, and here my y is equals to 6x power 5 plus 6, so I'm going to replace this y by this expression. So I just do it directly over here, because once when you try to use a graphic calculator and try to plot the curve of this quintic expression, quintic function, you are going to get a curve something like this. That's how it is going to look like. So this is going to be your minus 1 and this is your 2. So you see once when you just restrict it, so this is the area that you have to find out. That's what the objective is. Okay, So now we are going to use our normal integral formulas. So I'm going to do what? I'm going to separate out the terms, and I will apply my integration individually on these terms, like that. Here you see, always prefer to write the constant values outside and the coefficient values outside the integral, and at the place of the integrand you have to write the variable thing or simply unit, or what you call 1. Okay, so it's like that. Move it a little up. Okay, now you know that integral of a polynomial is equals to this thing. Okay, so plus some constant. So we are going to use this formula over here because this is something that you call polynomial function. So I am going to apply here my formula. Here n is my 5, so I just use my formula and write the values nicely. Plus 6 times, and you see here, as I'm having integrand 1, so whatever the variable you're having attached with the differential, on taking out the integration you simply write that variable over here. Okay, so that's it. Now it's gonna be something like that, and this 6 and this 6 will get cancelled. Now I'm just writing my limits right now as it is. In the next step I will apply my formula, which was f of b minus f of a. So you can see that on integrating original function I am getting new function in return. Okay, so I was integrating x5, I'm getting x6 in return. So this is my f of x, capital F of x. So now I'm going to apply my limits here. So I just use a big bracket, and I just apply the upper limit first. This is f of b minus lower limit, which is f of a. I hope it's clear. Plus 6 times, and then I apply my upper limit, which is f of b minus lower limit, forming f of a. That's how we do. So now what is left here is 64, and minus 1 power 6 is 1, so it is giving me this. Plus 6 times 2 plus 1 give me 3, so I'm getting here 63 plus 18, which is 81 square units. Okay, so you see, area bounded by this curve 6x power 5 plus 6 and these lines and the x-axis is equal to 81 square units. That's how we do using the formula. So how the formula has been derived geometrically, what was the scenario happening, I just tried to explain you everything, so I hope it's clear. Now we just move on and try to pick up our next example. Okay, now this is another beautiful example here. Now I need to find out area bounded by this curve. As you can see, this is a quadratic equation, so I'm going to have a nice parabola. So, and it is bounded by these limits. Okay, so here what I do in order to make it just for better understanding, I would like to show you here the graph of this function, how it looks like. So I'm just using here a Desmos graphing calculator. Also you can plot it on your own part using a notepad and all that. So I'm just using a graphic calculator here, and I just say that here my y is equals to 4 minus x squared. So you see, there's a nice beautiful parabolic curve here, and this curve, if I just further zoom for you, this curve is intersecting the x-axis at -2 and at +2. Okay, so at these 2 points the area is 0, so we need to find out area bounded by the curve from here to here and by the x-axis. Okay, so we just need to find out area bounded by this curve and the x-axis. The little mountain here, the little hill is here, whose area we have to find out. Okay, so we go back to the board and we just say that we are having a stuff like that, something like that, This is minus 2, this is my positive 2. I need to find out area bounded by this curve and the x-axis. Okay, so what it is going to be, we are going to use our nice formula of the integration, a definite integral which is going from minus 2 to 2, and f of x, that is y, is 4 minus x squared dx. This is actually going to give me area A, so I'm going to use it now. So I just apply my integral separately on the terms of my integrand, like that. And now here in the first integral, the integrand is 1, as you can see. So once there is nothing, it means there is 1. So that's what I'm going to get after integration. And over here I'm going to get x2 plus 1 upon 2 plus 1 is the x cube upon 3. That's what I'm going to get. This is it. Now we are going to apply our nice limits, upper and lower limits. So it is going to be minus 2. Okay, minus, I just write 1 upon 3 outside, and here I am getting 2 cube minus 2 cube. Okay, and I close it. So now I'm going to get my area within no time. So it is 4, and it's 2 plus 2 give me 4 minus 1 upon 3. It's just the basic maths we are going to do now. It's 8 minus 8. Okay, because you know, whenever you're having an odd power on a negative number, the answer is always negative. Okay, so negative cube is negative and 8 cube is 8, 2 cube is 8, right? So that's what it is. So it is going to give me 16 minus 1 upon 3, 8 plus 8. So it is giving me 16 minus 16 upon 3. So it is giving me 48 minus 16 upon 3. So it is giving me finally 32 upon 3 square units. So 32 upon 3 square units. You can write your answer in decimals and the whole number as well. It is going to give me 10 whole number 2 by 3 square units. Okay, so this is the area bounded by the curve, restricted by these 2 points minus 2 and 2. So I hope it's clear. That's all for today in this video. In the next video, I am going to discuss integration through substitution with a couple of examples. Hope you'll be with me. In order to gain access to the second video, I need you to click the link right at the bottom of this page, and that link is going to redirect you to my second video. Hope you'll be with me. Take good care of yourself. Allah Hafiz.